if I know that I have an abelian group of order 600 rather, then two possibilities for what that group could be isomorphic to are these two. What distinguishes those two choices one from another? So what's something that one of them has that the other one doesn't? What do you think? So which of these groups has an element of order 25? The second one. Where would I find that element of order 25? Yeah, it would be the generator, it would be a generator of this third factor, right? So has an order 25 element. And this other group does not. Okay. But maybe that's not enough. Maybe if we wanted to look deeper, we could figure out some other reason that these two groups are not the same. Give me maybe one more example of a abelian group of order 600 that's not isomorphic to either of these two. So we don't have to combine all the powers of the primes together. We could just sort of partially do it. So maybe take a pair of these Z mod 2s and combine them together into a Z mod 4. And when I say combine together, it's not really combining, right? I'm replacing it with a different up to isomorphism group that has the same order. Z3, Z25. And so now that's going to be different than the others. And what's interesting about that, so what's a way that I could use to distinguish, here's a good one, how could I distinguish this group from that group? What does one of them have that the other one doesn't?
Last one has an element of order, not an ordered pair because it'd be 3 terms in it, but 8, 3, 25. Whereas the next one won't.
And that would be an element whose order is the least common multiple of 8, 3, and 25. What is the least common multiple of 8, 3, and 25? I think it's 600, right? So actually, what's another way to say what the isomorphism class of this group is? Yeah, if it's got an element of order 600, it's the cyclic group, Z600. But that wouldn't be the case for this group, right? Because this 4 and this 2 are not relatively prime. I think the least common multiple here is going to be something like 300, I want to say. And so it'll have an element of order 300, but not an element of order 600. And so there's a difference between these two. But I think we can be even more basic than that. What about elements of order 8? Does this group have an element of order 8? How do I know? It doesn't, well, and moreover, the least common multiples of any factors of these are never going to give me an 8. Right? Whereas right here, I can see right away that in my ordered triple, right, a generator of Z8 and then the identity in these other two factors is going to give me an element of order 8 in that group. So your task in your small group is just to figure out how long does this list get? See if you can come up with a prediction and maybe a generalization, so a conjecture, for if I have any abelian group of whatever order, what is a way of figuring out how many different possibilities that there are? So work on this in your small groups for a few minutes and see what you come up with. How did you answer this question? So first of all, let's just take a quick go around the room. Each group tell me how many different groups up to isomorphism did you find that had order 600? Let's start with the group in this corner. 6?
Counting the original one.
Still working?
We had 7 counting the original.
6, 7, okay. 6? 6. All right, so let's go with the consensus of 6 here for a minute. So where did the 6 come from? So how did you get that 6 different groups?
Different combinations of the prime side.
Different ways of recombining the prime power factors with one another, right? So different ways of grouping the 2s together, different ways of grouping the 5s together. So how many ways were there to group the 2s? Yeah, there are 3 different ways. We can leave all the 2s separate. We can combine one pair of 2s together and leave the other one set apart. And then what's the third way? Just group all 3 of them together. Right? So there were the 3 different ways, right? They are all separate, or we combine 2 of them and leave one of them by itself, or we combine all 3 of them. How about for the 5s, before I go to your question?
Sorry, just a quick question.
Yeah.
Could you combine the other 2s and leave the other one separate, or is that the same exact thing?
That's up to isomorphism. That's a good question. Up to isomorphism, that's the same thing.
Okay.
Right? Because what group we would get if we combine the 2s in a different way is just the difference between Z4 direct product Z2 or Z2 direct product Z4.
Okay, it's the same thing.
Up to isomorphism, it's the same thing, right? Those groups are isomorphic one to another because direct products are symmetric up to isomorphism, right? So the elements of those groups are different because the ordered pair roles have been swapped, but there's an isomorphism between the two, which is all that we care about. So there's 3 different ways to group the 2s, 2 different ways to group the 5s. What about the 3? There's only one way. One way. There's 2 ways to do the 5s. And so how many ways were there in total? 3 times 1 times 2. That's the old multiplication principle from combinatorics, right? So there's 6 different groups of order 600 up to isomorphism. Yeah. You kind of think of it as how many 2s do I want to choose, right? I could choose to have all the 2s separate. I could choose the 4 and the 2, or I could choose just 8. Right, so those are my 3 options for how to group my 2s. And each one of those, I'm then going to say, what do I do with my 3s? Well, I only have one choice for what to do with my 3s. And then after I choose my 3s, I have 2 different things I could choose for my 5s, 5 and 5, or 25. And so the number of different paths through this tree is the number of different groups we can get up to isomorphism, which is 6. So there's 6 possibilities. So what does that mean about this nasty example? So we have to figure out all the ways, yeah. And then once I've figured out all the ways, I'm just going to multiply those together because they're independent choices. So for a couple of these, for at least one of these, we can do pretty quickly. How many different ways are there to group these 2 5s? Yeah, there's 2 ways. What about the 7 and the 11? There's only a single way. But it gets more interesting when we get over here to the 3s. Why did I put 11? Because it's 11. Oh, you're right. Yeah. I started writing a 1, and then I just got carried away and wrote another one. There we go. So what about the 3s? How many different ways are there to group together some numbers of 3s that add up to 4? The key word here that you may have heard in other contexts is partition. Anyone studied partitions before? So it's really a question of I have 4... let's say I have 4 siblings and I want to put them into any number of rooms. I'm basically deciding how to group them together into rooms, one with another, right? Which is the same thing as for each of the spaces, each of the gaps in between them, I'm deciding whether or not to draw a wall in that gap, right? So in between these 4 3s, there's these 3 little gaps. And if I want to, I can decide to draw no walls at all. And so I've grouped all 4 of them together. Or I could draw a wall in between each one. And now I've separated them all apart. Or I can draw just some of those walls and not the rest, right? So for each one of the gaps, I can choose a wall or no wall. So that's 2 choices. Another gap, 2 choices for that gap. Another gap, 2 choices for that gap. And every different way in which I can draw walls into those gaps gives me a partition of these 4 3s. And so there's 1, 2, 3 walls, 2 choices for each, so that's 2 times 2 times 2. I think that gives me 8.
But how many of those are different from each other?
Good question. Yes, exactly. Great question. Not all of those are different from one another, right? Because, for example, if I drew walls here, I'd get a pair of 3s and then 2 individual 3s. But that's the same thing as that I would have gotten if I drew them here instead, right? So I don't quite have 8 partitions. I actually have fewer than 8. So yeah, the question here would be how much repetition are there? How many different partitions represent, how many different ways of drawing walls represent the same partition? So there's a partition function in combinatorics. So once you account for all the different ways of drawing walls in between these that give you the same partition at the end of the day, it turns out that 3 of those are the same as one another. We can eliminate them from this total of 8. And so the partition function applied to 4, so the number of different ways of partitioning 4 into a sum of non-negative or sum of positive integers, it turns out to be 5. So there's 5 different partitions, so 5 different ways of grouping these 3s together up to our isomorphism. And then I have 8 total factors of 2 over here, and it turns out that there's 22 partitions of those 8 powers of 2. And so at the end of the day, I multiply all those partition numbers together, and I end up finding that up to isomorphism, there are 220 different abelian groups that have order equal to 39,916,800. So the key here is that the fundamental theorem of finite abelian groups is what tells me that these are the only ways to create the groups of the orders that we want to. So we take the prime power factorization, and then for each repeated prime power, we ask how many different partitions are there of that number. And so if you want to take this to the bank, we can say that the number of groups of a given order, abelian groups of a given order, is equal to the product of the partition numbers of k sub I, where the k sub i's are the exponents that appear in the prime factorization of our number. So in other words, in our example here, it was the product of the partition number of 8, the partition number of 4, the partition number of 2, and the partition numbers of 1, which are always just 1. So the way to get large numbers of abelian groups is to have large exponents in the prime factorization of that number.